Hello, and welcome back to What Is. Today, we're addressing a huge question, literally, the biggest question you can ask. What exactly are you standing on right now? Is it a solid, eternal rock? A foundation that will never change? Spoiler alert, absolutely not. The ground beneath your feet is a giant, slow-motion disaster waiting to happen. It's a collection of massive, rigid slabs floating on molten goo, and it's constantly shuffling itself like a massive, geological deck of cards. We are talking about plate tectonics, the continental conundrum for most of human history. We looked at the massive continents and assumed they were permanent fixtures. They looked solid, they looked heavy, they looked like they weren't going anywhere. But then, you look at a map, and suddenly, things don't look so solid. The shape of South America looks suspiciously like it could nestle right up against the shape of Africa, like two long-lost jigsaw pieces. In 1912, a German meteorologist named Alfred Wegener looked at this puzzle and said, "Wait a minute." They were together. Wegener proposed the theory of continental drift. He pointed out that fossils of the same ancient species were found on completely different continents, separated by thousands of miles of ocean. He noted the distribution of ancient tropical coal deposits in places like Antarctica. His conclusion: all the land masses were once one supercontinent, which he dubbed Pangea, meaning all lands. Wegener was a genius, but his peers thought he was raving mad. Why? Because while he proved that the continents drifted, he couldn't explain how. What force was powerful enough to shove entire continents across the globe? It took another 50 years, and the mapping of the ocean floor during the Cold War for science to catch up. And that is when continental drift evolved into the much more powerful theory we now call plate tectonics. The magma conveyor belt. The key difference between drift and tectonics is scale. It's not just the continents that are moving it, it's the entire outer shell of the Earth, known as the lithosphere. Think of the Earth like a hard-boiled egg. The crust is the fragile shell. But the lithosphere includes the crust and the very uppermost, rigid part of the mantle. This combined shell is broken up into about 15 major plates, plus dozens of smaller microplates. And what are these plates floating on? The asthenosphere. The asthenosphere is the gooey layer below the lithosphere. It's not liquid like water, but it's hot enough around 2,400 degrees Fahrenheit that it behaves plastically like extremely thick, slow-moving taffy. And here is the magic mechanism: convection. Deep within the Earth, the core generates immense heat. This heat rises, causing the molten rock in the mantle to circulate. Hot material goes up, cools off, and sinks back down. This creates giant, slow-motion currents, much like the circulation inside a massive lava lamp. These convection currents act like a geological conveyor belt, dragging the rigid tectonic plates above them. The great news: we are not zooming across the planet at highway speeds. Tectonic plates move about 1 to 10 centimeters per year. That is roughly the speed at which your fingernails grow. So, don't worry about falling off your couch mid-sentence. Crash, burn, and grind. The real geological action happens where these plates meet. These are the boundaries, and they determine everything from where we build our ski resorts to where we hide from the shaking ground. There are three main types of plate boundaries, and they are defined by how the plates interact. First, we have divergent boundaries. This is where the plates pull apart, separating from one another. As they separate, molten rock, or magma, oozes up from below to fill the gap, creating new crust. The most famous example is the Mid-Atlantic Ridge, a massive underwater mountain range spanning the entire length of the Atlantic. It's essentially a 10,000-mile-long volcano, constantly printing new ocean floor, pushing Europe and North America farther apart, inch by inch. Next, the most dramatic interaction, convergent boundaries. This is where plates smash together. When an oceanic plate which is denser collides with a continental plate which is lighter, the oceanic plate sinks beneath the continent in a process called subduction. This subducting plate melts, generates magma, and fuels the creation of volcanic mountain ranges, like the Andes in South America. If two continental plates collide, neither plate wants to sink. They buckle, fold, and thrust upwards, creating the planet's most immense mountains. This is how the Himalayas were formed, where the Indian plate is currently headbutting the Eurasian plate. Finally, we have transform boundaries. This is where plates slide past one another horizontally. They don't create new crust, and they don't destroy old crust. Instead, they just cause friction. The plates get stuck, stress builds up, and then they suddenly slip, releasing enormous amounts of energy. The shaking you feel, that's an earthquake. The most famous transform boundary in the world is the San Andreas Fault in California, where the Pacific plate is trying to scrape past the North American plate. Good luck, California. Plate tectonics isn't just a quirky geology fact. It is the unifying theory of Earth science. It explains why volcanoes erupt, why earthquakes happen, why we have oceans, and why the planet's continents look like they've been rearranged by a very patient, very powerful giant. The Earth is not a static rock. It is a dynamic, living system, constantly being recycled and reshaped, driven by the fiery engine in its core. It is the reason we have habitable land, and the reason Pangea will eventually assemble itself again in about 250 million years. Thanks for joining us on What Is. If you enjoyed learning about the Earth's greatest puzzle, please like this video, subscribe to the channel, and let us know in the comments below, which tectonic plate are you standing on right now? We'll see you next time.